Okay, so round two, we have Albert Law, who's going to tell us about soft scalars and the geometry of the space of celestial CFTs. Take it away.
Hello. Okay. Hi everyone. First of all, I want to thank the organizers who invited me to speak. It's been a very enjoyable workshop at Corfu here. So yeah, the title of the talk is soft scalars and the geometry of the space of celestial CFTs. And this is based on this recent paper with Dan and Shruti, who are also in the audience. So yeah, let me start by saying well, a lot remains to be understood about the operator content and abstract characterization of celestial CFTs. So one common method to investigate an intractable system is to study the space of possible deformations of the models. In the context of celestial CFTs, global conformal symmetry corresponds to Lorentz invariance in the bulk. So we don't expect that they are violated. So we are interested in deformations that preserve conformal invariance. So in other words, we are led to study the space of exactly marginal deformations or the conformal manifold of CCFTs. So in standard examples of ADF CFTs, conformal manifold of the dual CFT correspond to bulk moduli space of vacuum. And we'll see that a version of this correspondence also holds in the context of flat space holography. In asymptotically flat space, families of inequivalent bulk vector are actually relatively common in models of quantum gravity. They appear as scalar and complex moduli space of super string compactifications. So yeah, this is the most important slide of this talk. Yeah, so you will see that, well, yeah, the point will be that, first of all, bulk vector can be identified with boundary conformal manifold in this context. And statements of soft theorems for fluctuations around a point in a bulk vector equivalent to statements of exactly marginal deformations of CFT correlators. And yeah, this is the picture. Okay. All right. So yeah, just to set the stage, let's review a little bit. Oh, yes. Yes. Oh, just in the space of vacuum in the bulk can be identified with conformal manifold on the boundary. Oh, we'll see. Okay. Yeah. That's something it's gonna. I'm gonna explain. Yeah. I just all right. Definitely not trivial. Okay. So yeah, just to set the stage, let's review a little bit how just to set up the notations, everything in aperture dimensions. Okay. So yeah, all of us knows that Lorentz generators in the D+2 dimensions, you can rearrange them by taking these linear combinations, and then you see that the Lorentz algebra is the same as the Euclidean conformal algebra in D dimension. Okay. And then we parameterize on-shell momenta in this way. So here, these Q's and N's, they are null vectors, and these X parameterize the coordinates on the celestial sphere, right? So bulk Lorentz transformations are realized as boundary conformal transformations on the X coordinates. So S matrix is defined to be the overlap between in and out scattering states. And n particle scattering amplitude takes the following form. Okay, so if we define these operators, then the amplitude can be written in this very suggestive form. But the thing is, these operators, they are not. Yeah, the dilatation is not diagonal in these spaces. To diagonalize that, we can do that by doing a Mellon transform like this. Okay. So the resulting the correlation functions of these operators, they will transform as conformal correlators in the Euclidean CFTD. Okay. So for the choice of contour here, a lot of works take the contour to be non-compact, lying on the principal series. But obviously, it excludes the integer value dimensions that includes very important operators such as stress tensor and conserved currents. So, a number of works actually shown that we want to include those operators. So these can be obtained by doing these compact contour, extracting residues. And these operators, they are intrinsically tied to soft scattering states because essentially what they're doing is isolating individual terms in the soft expansions of scattering amplitudes. So for example, this is the soft photon operator. Isolate the Weinberg pole in the abelian gauge theory. And another example is subleading soft graviton operator, isolating the subleading order one term in the soft graviton expansion. So these operators, they're interesting because they're related to the conserved currents and stress tensors through the shadow transform. Okay. So just a reminder, a shadow transform maps a conformal primary of dimension delta and spin s to an operator of dimension d minus delta and spin s. All right. So generally, for an operator in some representation of the SOD takes the following form. Okay, this is essentially a two-point function. For example, for scalar, it's simply this. Okay. All right. So if you apply the shadow transform twice, then that is equivalent to applying it's proportional to the identity with these coefficients. So if you take the shadow transforms of the leading soft photon operator and the subleading soft graviton operator, then the resulting operators, they satisfy the wall entities for a conserved current and stress tensor respectively. So later we'll see that we'll actually see a spin zero analog of these. All right. So now is the third part. Like I said earlier, families of inequivalent bulk vector, they are relatively common in models of quantum gravity in asymptotically flat space. These bulk moduli space, they are parameterized by vacuum expectation values determined by boundary conditions of local fields at spatial infinity. And the long wavelength fluctuations around these vacua, they are described by sigma models, okay, with the target space given by the vacuum manifold. So now, it's time to introduce the sigma model. Sigma model is defined as a functional integral, is mapped from the Minkowski space to the vacuum manifold. All right. In more than 2 dimensions, the model is non-renormalizable, but this is the minimal action. And so here, these fields phi, capital phi, can be thought of as coordinates on the vacuum manifold, and this Gij is the metric, okay, which must be Riemannian if you want to have correct signs for kinetic terms. All right. So yeah, like I said earlier, the modular space of bulk vector is parameterized by boundary conditions of local fields at spatial infinity, right? And here, the second point is the Hilbert space, and for each point on the modular space, you have a corresponding Hilbert space and the set of operators. So that means, in other words, the Hilbert space and the operators of the model vibrate over the vacuum manifold. So yeah, this is the picture for every different points, you have different Hilbert space. So to do perturbative calculations for a sigma model, you expand the fields are about their depths like this. Okay, so this is a background, and you have some fluctuations. And then in Gaussian normal coordinates, then the action becomes this is the first few terms in the expansion. So yeah, in particular, you don't have any cubic term. So here, this is the covariant derivative on the modular space, and here this is a Riemann tensor. And it's important to note that the Riemann tensor and their derivatives, they are functions of the vacuum expectation values, right? For example, the three-level 4-point amplitude for these modular scalars, they can be written in terms of the curvature like this, and the 5-point is the derivative of the curvature, right? So the soft, you can consider soft theorems for these modular scalars, and they will take, this is the form of the single soft limits. Okay, and here this bracket, the subscript D indicate that it is computed with the boundary condition where the expectation value is V, all right? And again, this derivative is acting on this amplitude as a function of the expectation value, right? So this motivate the definition of this leading soft modular operator in like this, okay? And it is essentially the spin zero analog for the leading soft photon and the subleading soft graviton operators we saw earlier. And notice that this operator has a conformal dimension 0, okay? And in terms of this, then the single soft theorem, take this following form, okay? And notice that this guy is essentially a topological operators. The matrix element, they are independent of the position of X, all right? Yeah, for example, you don't have, you don't see any X dependence on the right-hand side, okay? However, if you have multiple insertions, they might contain position dependence, right? Because this operator has dimension 0, it can be thought of as a shadow transform of a marginal operator, okay? And this is how you should think of these soft modular insertions. Because the fluctuations describe the long wavelength variations of the vacuum expectation values. So the 0 modes can be thought of as shifting the expectation value, right? So the single soft theorem is basically the statement of an infinitesimal transport on the space of vector. Yeah, like that, okay? Yeah, for a finite deformation, then you want to exponentiate what you saw earlier. And then, but then because the modular space is in general not flat, then actually, you need to have some path ordering, okay? Right. For example, you from the pictures, yeah, that in general there should be some non-trivial holonomy inside this loop. So yeah, you need to specify a path. Okay. Yeah. Determine the connection of what? Sorry. What determine curvature? You have a metric. You have a metric. Then you can compute. Well, that depends on the detail, right? How you get these sigma models, right? Yeah. It's a kinetic. Yeah, right. Is that what you're asking? Well, I'm just not sure. Yeah. Okay. Yeah. All right. Yes. Oh, there is no correct path, right? Because it's just like comparing tensors on a manifold. There is no. Yeah. 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 Right. So yeah, now right, if we take the path to be an infinitesimal loop, right, then supposedly that will capture the curvature, right, of the connection, and this is basically captured by the anti symmetric double soft limit like this. Okay. Yeah, and these papers, this paper they shown that it's really just that. It also just follow from the definition, right? From the yeah, you can express this in terms of these residue operators we shown earlier. Just define a contour in this way. Basically, the analog of the radial ordering in the CFT2, right? Okay. So this is the right. Yes. Yeah. No, I'm just saying, yeah, this statement, you can map it to the surface, right, by doing contour. Yeah. The next slide is the next slide is a condition. So this you got from the geometry of this. Yeah. Oh no, this slide is really just rewriting them in terms of the S, we showed earlier. Right. Like, yeah, I'm just saying, yeah, the contour should be taken. Yeah, right. Yeah, right. So here is just a comment on the. Yeah, we know that double soft limits, they in general they don't commute, right? And from what we've seen, right? That's non-commutativity of this double soft limit is basically reflecting the non-trivial curvature of the moduli space of vacuum, right? So that means different choices of soft limits, they will correspond to path dependence of parallel transport of the S matrix in this space. Okay. In other words, the ambiguity of double soft limits, they're basically the same as the ambiguity of comparing tensors at two different points on a manifold, right? So from this point of view, it's not a problem, it's a feature. Okay. Yes. Yeah. Different Yeah. I'm not, yeah, actually, I'm not exactly sure how to think about the simultaneous. Right. Yeah. Right. Yeah. Right. All right. So yeah, and this ambiguity, right? They have a well-known analog in non-Abelian gauge theory and gravity, right? And I believe Dan will elaborate on that, right? Yeah, and now let's connect what we just saw to conformal perturbation theory. Okay, so so here we are just is purely CFT, right? The abstract characterization of a CFT, first of all, is the spectrum of local operators, and then second, the collection of the OPEs, right? Coefficients. So the spectrum of local operators might contain a subset of marginal operators with spin 0 and dimension d. In which case this combination is formally conformal invariant. And from this expression, you can think of them as the shadow of a marginal operator, right? And if the original CFT has a Lagrangian description, you can deform the model by adding this term, right? So this is the original action, and you can deform the model in this way, right? Right. If the original CFT is non-Lagrangian, then the observable in a deformed theory can be defined simply like this, right? Again, in general, this space of conformal manifold can have curvature, so you need to specify some path dependence here, right? Right. So right, since this operator has dimension 0, then the deformation might preserve conformal invariance. But of course, generally it might not be the case. But if it does, that means these operators, they are exactly marginal, right? Then these deformation parameters, they can be thought as coordinates on the conformal manifold, right? Yeah, this is the comment I made earlier. This exact marginality is not guaranteed. Okay. Right. For small lambda, for the small deformation parameters, you can approximate the deformed correlators using this series, right? But the convergence of this series is not understood even in standard CFTs. Right? But yeah, one point is that because correlation functions they are singular at the coincident points, then the right hand side, right, each term they are typically infinite and needs to be regulated, and that would introduce some scheme dependence, right? So if to the first order in the conformal perturbation theory, you just expand what you saw earlier, like that to the first order. And then for infinitesimal deformation, then you see that the insertion of this operator is same as taking into covariant derivative. So this is basically the same thing we saw earlier, right? Right. So yeah, it's basically the same picture. The first order deformation is basically implementing infinitesimal translation on the conformal manifold, right? Yeah, here just showing you again, you compare with the single soft moduli theorem we saw earlier. Right? Yeah, and similar to the right, similar to the bulk, right? The correlation functions, they are generally tensors on a vector bundle over the moduli, over the conformal manifold, right? And parallel transport around an infinitesimal loop will measure the curvature. Okay. Yeah, again, it's the same picture as before, right? And again, you should compare this with the anti-double soft limit, right? Yes. Yeah. Yeah. Yep. Yeah. Then we'll talk about that. Yeah, there were functional derivative. Yeah. Yeah. Right. Okay. And any other questions? No. Yeah. So since I don't have much time, I will just describe a little bit here. Right. So yeah, when there are exactly marginal operators, the intrinsic geometry of the conformal manifold can be described using just the CFT data. All right. And this was studied in this paper by Kutuzov a long time ago. For example, the two-form function of the marginal operators, they compute the metric on the conformal manifold, right? And similarly, the connection is computed by an integrated 3-point function, I think. Yeah. Yeah, and right, and this integral is divergent and needs to be regulated. And we are free to pick a scheme where this thing vanishes just identically. And this is basically the analog of choosing Gaussian normal coordinates in the sigma model. And similarly, for the curvature, Riemann tensor, it can be obtained by twice integrated four-form function, right? Like that. And you need to take this particular linear combination, right? And here, there is a calculation that we did, is to try to think of this as a four-point function of two marginal and two shadow operators in CCFT. Okay. So yeah, we computed a quantity that is analogous to what you saw in the previous slides in the following way. So recall that the three-level four-point amplitude for these modular scalars take this form, right? So if you're right, taking the Mellon transform, right, it's doing this. And if you do this rescaling, you'll observe that this omega 4 integral will lead to this delta function in deltas, right? And we call that we expect the Riemann curvature should be related to a correlators of two delta equals D and two delta equals 0 operators. But apparently this is forbidden by this delta function, right? However, yeah, one way, yeah, to get around that is to first of all compute the non-vanishing four-point function with one delta equals D and three delta equals 0 operators, and then you take the shadow transform on one of the delta equals 0 operators, right? In other words, we are computing this thing, okay, and we will yeah take this delta 1 equals 0, 0, 0, D, for example, right? Yeah, so it turns out different choices of operator dimensions can lead to finite or infinite results depending on the specific kinematic configurations. For example, if we consider epsilon 1 equals epsilon 2, right? That means, right, particle 1 and 2, they are both ingoing, and the 3 and 4, they are both outgoing. Okay. Then you see that these two correlators, they are finite. So if the particle 1 and 2, they're taken to be both dimension d, and the other two to be both 0, or the other way around, then they will be finite. Okay. And here I'm expressing in terms of the d-dimensional cross ratios. Right. And for example, if you take 1 and 3 to be ingoing instead, and 3 and 4 outgoing, then this combination, this will be d 0, then that thing is finite. You know, the patterns go on and on. Anyway, so if you take this linear combination, then the resulting quantity is indeed proportional to the Riemann tensor. All right. Right. See, it's just an example. Well, of course, except you know, this factor is finite. So, but actually, this actually arises as another, well, at the level of momentum space amplitude. This is the origin of, you know, why you have this proportionality, right? Similarly, the covariant derivative of the Riemann tensors is related to the 5-point functions of the marginal operator integrated 3 times. Okay, and you can do the same exercise, and then the operator dimensions, they always work out similarly. Right, you always need to shadow one of the legs. Okay, and even higher points, you have this, all of this generalizes to a higher point corridors as well. Anyway, so I'll end with these slides, which you already saw earlier. The key message of this talk, first of all, bulk vacua can be identified with a boundary conformal manifold, and the second, soft theorems for fluctuations. They are basically statements of marginal deformations of CFT correlators. This is the picture. And that's all I want to say. Thank you. But it's not guaranteed they preserve conformal invariance, right? I'm not sure about that. Sorry. The what? Yeah. Oh, it should depends on V too. Right, that depends on the you need to pick a base point, right? On the conformal manifold. So yeah. They are on the principle here, so it doesn't depend on this, doesn't depend on the old or where at the level of the amplitudes, those V dependence they're in the curvature, right? Yeah, I think so. Yeah. 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 Also, two-form functions, right? They're related to the metric, for example. Then the metric depends on the
Okay, let's thank Albert again for a very stimulating time. And we'll have a half-hour coffee break now, and then come back at 11, where we'll start with Dan.